Okay, chapter 14, Basic Chemistry of Pearson. This chapter will also have work sessions that will not be in the recording. So this recording is only the lecture part, not the work sessions. Acid and bases, and so you see the outline shown here on the slide. We'll go through acid bases, Bronsted Theory acid bases, strength of acid and bases, dissociation constants. You can guess what those are going to be, right? Products or reactants again. Dissociation of water is going to be products or reactants. The pH scale, reaction of acid and bases. You know how to balance equations, you know how to do reactions, and you now know how to do reactants over products for equilibrium, acid titrations. You know how to find moles, right? And you know how to find molarity. So you will be able to do these. And if all else fails, you will do them by a dimensional analysis. All right, so let's take a look here, and this will be at a pretty good pace, but we will work through these, and we will post some other things to help you work the problems, okay? Acids have a sour taste. Change blue litmus to red. Corrodes metals. Ionize in water to produce H+, and this is a key. Ionize it to produce H+. That's what makes it acidic. So that's what it looks like. And so if you had to write, could you write a KEQ for this? Can anyone write a KEQ for this? How would you write it? Products over reactants. With brackets around it to say concentration. You get it? So KEQ would be H plus Cl in brackets divided by HCl in brackets. That's how we write these over and over again. Products or reactants. Yes, sir.
You said H plus Cl. It's not. It doesn't have the negative on it either.
It'll have Cl minus.
Oh.
It'll be Cl minus. Yep. So it'll be this in brackets, divided by this in brackets. Okay. That's how we write them over and over again. And so here we show the names of common acids and their ions. I do expect you to know hydrochloric acid. I do expect you to know nitric acid. I do expect you to know sulfuric acid. Got it? These are very common and are used a lot. Okay. Phosphoric acid is another one that's used in a lot of buffer systems. Okay. Yes, I expect you to know what they look like when you see them. Okay? All right? HCl stomach acid, HCl environmental acids, and sulfuric acid environmental and battery acid. The Arrhenius bases, and these are all just names of these. Got this? Okay, you follow? I expect you to know the concepts. Produces hydroxide. So the acid produces H+, the base produces OH-. Hydroxide. So everyone follow. That's how you'll know them. So if you see an equation and you see OH-, it's a base. If you see an equation and it's H+, it's an acid. That is what I'll expect you to hang on to and know. If it has an H+ in it, it's an acid. Excuse me, OH-, it's a base. And this shows you some of the properties of them. Excuse me. All right? And you put an acid with a base, it makes a salt. It gets neutralized. Hydroxides containing bases ionized in water to produce hydroxide and a balanced equation. Can you write the KEQ for this? Does anyone know to write? What would I write for the KEQ for this one?
Two OH minus, or
No.
OH minus,
OH minus
and then over
raised to the 2. Remember? The 2's, right? I don't know if this pen works or not. I hope it does. So we would write KEQ or KSP or whichever. Okay. We'll just take K for now. general K calcium plus 2. And this is what? OH minus. Get it? Raised to the 2. What do I do with the other side? That's products. What do I do with the reactants? Do I write them?
No, because it's solid.
No, because it's solid. You got it then. I'm happy. Okay? Follow? It's always raised to the coefficients. Divided by the product. It's a solid. We don't write the solids. You have it. Very good. So here are some examples of them. So if you see OH on it, it's going to be a what? Base. If it leaves off with H, it's going to be a acid. Okay? Here we show you what's called the hydronium ion, and this is what we write it. It's H3O plus. We typically, so if you see H plus or H3O plus, for all intents and purposes, that's the same thing. So watch for it. For all intents and purposes, you see H plus or H3O plus, they are the same. We did it because it actually exists as a hydronium ion. Okay, this is how it actually exists, but occasionally we write it simply as H plus. With me so far? And it's plus and it's AQ, that means it's a free ion. If it's a free ion, it has the potential to conduct electricity. Whether it's weak or strong depends on where it is on the periodic table, because that determines its dissociation, the degree to which it will dissociate all this. Okay? A solution of hydrofluoric acid forms a hydronium ion. So how would I write this one then? This would be an AQ behind it, right? So what would I write for the KAQ? I would write H3O plus in brackets. No, and there's no coefficient, so we're good there, okay? And I would write Cl minus in brackets. This is liquid, okay? And this is gas. So I would have divided by what? HCl. Not water because it's what? Liquid. Okay? Very good. This is what we do over and over again. And the concept here really is to help you to understand the impact of ions in our environment. They are a significant part, and they're a critical part of how and why we exist, and particularly biologically. Okay? So here we show you ammonia in water. This is going to be AQ, AQ. I know it because it's showing the plus and the minus. I'm going to write the equilibrium. Here I'm going to write it divided by what? Ammonia, not water, because it's water. Here, according to Bronsted theory, an acid donates a proton and a base accepts a proton. Simply memorize that for me. This is what we've been talking about. So Bronsted, it has a proton to give up. Okay? And a base accepts a proton. That's how Bronsted, that's how he defined it, and that is the definition that we live by. Okay? So we expect you to memorize this definition on slide number 10. Okay? We're okay? I'm sorry? Oh, you good? Okay. Here, this is a concept you've not heard. And when I test you on this concept, the answer will be there. You'll have to make the choice. So learn the concept. I won't be asking you to write them. I'll be asking you to identify them in this class. Okay? And these are called conjugate acids and conjugate bases. HF, an acid, loses a proton to form its conjugate base, F minus. Water acts as a base by gaining a proton to form its conjugate acid. So this is the acid, okay? And the acid goes to its conjugate base. Does everyone follow? So if you have the acid goes to a conjugate base. The base goes to a conjugate acid. You follow? They go just the opposite. It's a weird concept for people alive. For over the years I discovered it. For whatever reason, this concept bothers students. So you might have to find your own way to make it make sense to you. Okay? But here's the bottom line. You'll start with this acid. Okay? the you always write compounds as electropositive, electronegative. We've taught you that already. So the electronegative part of the acid is its conjugate base. You get it? So you simply look at it here and find it. Okay? This is the acid. Can you identify the acid? We're okay identifying the acid? It's going to start with H. Then look for this part. That's the base. Find the acid first. Okay. The other part's going to be the base. This case, so since you know this is the acid, this must be the base, right? So go to the other side and look for where that proton is sitting. It's going to be the conjugate acid. This is important to equilibrium because when things don't work just well, species are added to balance these, and knowing that one's a conjugate base or a conjugate acid is important to how that balance and how the solutions are made balance it. Okay. So you might have to find your own way of memorizing it. I don't have any unique tricks for this, and I've taught this a lot of years, and about 50% of the students get it right off the bat, and the other 50% say, I'll find a way to memorize it. Okay. So just making you aware of it. So if you're struggling with it, you're not alone.
So what kind of question would you do that?
I would ask you, where's the conjugate base?
Oh.
I'd give you this acid, and you'd have these two choices. And I'd say identify the conjugate base. You would identify it by looking at the acid. It's going to be this part of it related to it. Could you ask that? Here, show you again. Okay? So, this case, this is the acid, and it's going to the conjugate base. Follow? This is the base, and it's going to the conjugate acid. Conjugate just simply means it's this pair. It pairs with this. Okay. So take a look at these, and take a look at the textbook. He gives some unique ways of thinking about it too. And I've read a lot of textbook, and I haven't found anyone yet that can do it where it really gets everybody. So one of those concepts is challenging sometimes. Okay. And if I explain the principle to you 100 more times, you may be in the same boat. All right. The strength of the acid is determined by the moles of the proton produced in the moles of acid dissolved. The strength of the base is determined by the hydroxide. So what is it I really expect you to hang on to and know here? I expect you to be able to identify an acid and a base. Okay? An acid depends on its proton strength. A base depends on its hydroxide strength. Get it? I expect you to know that concept. All right? The math in this will be KEQs given to you already on the exam. Okay? So here we show you this is an acid and a base. You get a conjugate acid, conjugate base pair here. Okay, this is the conjugate base of HCl. So everyone see that? Because I see it here. This is the acid. I know HCl is an acid. Cl minus is the conjugate base. Okay? Okay? So everyone see that? This is a base, and this goes to the conjugate acid. And the arrow's in the wrong place. So there's 6 strong acids in water. We show you here. And I think I gave you hydrochloric, sulfuric, and nitric. These are the 3 that we ask you to focus on. Okay. All right. So strong versus weak. Here, a weak acid. This is acetic acid. Yeah, this is acetic acid. It's slightly dissociated. This is a pet peeve of mine. Well, I hate the way he writes this. Okay, I got it off my chest. End of that story. All right, so here, typically when we write this as an organic chemist, the guy who wrote this was not an organic chemist. He wouldn't have written it like this. He would have written it with a proton, where the proton was attached to the oxygen so you could see it better. Okay? In this particular case, you can't see that this hydrogen is attached to the oxygen, not to the carbon. So, okay? So here, this is an acid. It's a weak acid. If it's a weak acid, does it conduct electricity strongly or weakly? Weak or strong electrolyte? This is a weak acid. Is it a weak electrolyte, a strong electrolyte? That's correct. Sounds too easy, doesn't it? If it's a weak acid, it's a weak electrolyte. If it's a strong acid, it's a strong electrolyte. That's why sulfuric acid is used in car batteries. Okay? So here we have strong acid dissociates. If it's strong acid, it makes what type of electrolyte? Strong electrolyte. So here, yeah. So we have these weak acids. They only partially ionize, and that's what we mean by here is an equilibrium. There are many weak acids, and they are showing you here. Most of the ones that your fruit acids are weak acids. Okay, hydrofluoric acid is the only halogen acid that is a weak. This is a unique one. So keep aware that HF is a weak acid. It'll fool you because you think it's in group 17. It should be strong. It is not as weak. Okay, all right. So this is one you simply have to be aware of. The purpose of this lecture is really exposure to acids and bases, over and over again. Got it? And that's what you're going to hear over and over again. And now you know how to do the KEQs. It tells you how to get those concentrations. At the end of this lecture, you're going to see why getting those concentrations is important. Okay? So here we show you strong versus weak again. I don't expect you to memorize these. I've already given you ones that I expect you to really know for me. Hydrochloric, nitric, sulfuric. We expect in terms of bases, I should give you those. Sodium hydroxide, potassium hydroxide are the strong ones I expect you to know. Okay? Potassium hydroxide, sodium hydroxide are the strong ones that we always use. And lithium hydroxide. Those are the bases. So if you see those, they're going to be strong. Lithium hydroxide, sodium hydroxide, and potassium hydroxide. Relative strengths of acids and bases. Here we show you all of them. Well, this group here. Okay? Don't expect to memorize these. Be familiar with the ones we've given you. Strong acid bases dissolve completely in water, producing a high concentration of ions. If it produces a high concentration of ions, strong or weak electrolyte, there you go. I'll keep saying that because that way we can reinforce it. You guys have seen this before, right? Writing the association constant. You know how to write them. You see it's what? AQ, AQ. Therefore, I can write the concentrations. And here, you know, I only have what? This one here. Why don't I have water? Because of what? Liquid. Okay? So this we will expect to be able to write these. A large Ka or Kb value for the acid or base. The larger the ratio of the product to reactant. You know this now, right? If it's large, that means wow, it goes to the product side. If it's small, it goes to the reactant side. Your fruit acids lie on the reactant side because they're weak. Okay? Your KOH and sulfuric acid, they lie on the right side because they're strong. Now you get it. Ka, what do you think the H stands for? Acid. There you go. Kb, base. So, but how do you do the process the same way? Yeah. You just do one with the acid, one with the base. You get a value for acidity and for basic. And I think you intuitively know there's a difference in acids and bases. Yeah? Kind of right? Okay, like there's a difference in vinegar and cleanser. Right? You know that. Okay? So you can write the balance equation again. Now you see all this stuff is coming back to see us near the end of the semester. All these great things you've been learning and been excited about this entire semester. Right? Yeah. It's coming back to see you. Balance equation. And we right away pay attention whether it's AQ or not. So which of these is going to fall out of the equation? There you go. Right? Water here. And we write the equation. If we have the values for these, what do? Put them in, punch it. What do we do with the units? None. There you go. What if I gave you moles and I gave you liters? Could you get it?
Yeah.
Because it's moles per liter. You get it? If I gave you grams, could you get it?
Yes.
Yes. You take grams Send it to moles through the dimensional analysis. Now you got moles divided by the liters. Okay? And you do that over and over again. Lots of fun for chemists. In pure water, a forward reaction between two water molecules transfer a hydrogen ion. Basically, this is telling you that water itself, okay, looks like hydrogen ion and hydroxide ion. Okay? That's what water itself looks like. So we have hydrogen ion and hydroxide ion reverse reaction to reform water molecules. So this is the equilibrium in water, and this is how we like to write them. So this is H3O plus, which is the same as saying H plus. So everyone follow that. Okay? So we write it as AQ, so we write the equilibrium. But look, note here, does any of this get written? No, because it's all liquid. So therefore we call it KW. What do you think the W stands for? Water. Now you get it? We're just using equilibrium constant over and over again, and we're denoting what species we're doing it with. And now you know that you can't put water over water, right? Okay? This next concept that I'm about to show you is very important to hang on to, because we're going to move into pH. Because now when you do the KW, does everyone see why this is a KW? Right, this side divided by this side, but you don't write this because it's liquid or solid. So KW. And that means we can now rearrange this equation for those of you who like to can do the rearrangements, and it's important that you be able to do it, or you be able to plug it in here and punch it through. Okay? All right? And yes, I have adjusted some of my acceptance of the math. Okay? So if you put it in here and then you punch it, I'm going to be happy. But I have to see them in the equation. You get it? Okay? It looks like some of you know how to auto punch it once you get it put in here, and that's okay. I'm not going to sweat that. So we have this. And because of that, we can do calculations. Vinegar solution has hydroxide of 10 to the 12 at 25 C. What is the hydrogen ion concentration? It has what? Hydroxide here, so we can calculate it. KW has a set value, and it's 10 to the 14. That's a standard constant. Okay? And I will give you that on the exam to remind you what it is. So you simply put it in the equation. See how we have the equation set up here? You can rearrange the equation to do it. We substitute in the values, and we get this. Or if you like, you can put the value in here and punch it through. Okay? So rearrange equations, cool. It really works. It shows more. It brings more clarity to it. But it appears that doing the rearrangement is tripping some of you up. Particularly, you seem to be able to work it from here, so I can live with that. Okay? So substitute in the known hydrogen ion concentration. And voila, we get this. Does everyone understand this part? This is Barrett plugging it through, pushing it through. Any questions there? Okay? You understand that KW is a constant. 1 times 10 to the minus 14. Never have to think about that. Never calculate it at all. It's simply a known constant. Okay? And so we just take this equation and we put in the value that's missing. Solve for the missing value. Memorization. Ready? And this is something I think most of you already intuitively know and have known by now. pH solution is used indication of acidity of solution. It has a value of 14. Don't lose sight of that as 14. It doesn't go higher than that. You do any calculations and it doesn't sum back up to 14, pH and POH, and it's higher than 14, you are wrong somewhere. It's always 14 or 10 to the 14. That's it. That's the max. Get it? 10 to the minus 14. Okay. So acid, pH is less than 7, neutral is 7, and base is greater than 7 for pH. I think you know that. So everyone has never seen this concept before. Most of you have at some point. You kind of know that. Note the values, 10 to the minus 17. These values are always going to be to the negative. You want, okay, if you see to the positive, get concerned. Going to be to the minus. To the minus 7. And this is why it's 7. Okay. Here we show you some examples of some common acids. I don't expect you to memorize these. It's just kind of one of those healthy things to be familiar with. Okay. I think you guys did your pre-work dealt with this because I had some of you tell me what you ate and all that and where it is, pH and all those things. So you see pop is acidic. Here we start to get cheer. Seawater is a little basic. You can taste it when you do it. Here you get really basic. Okay? And here's where we have to learn to do the calculations. And you will want to practice these on your calculator at home a few times. I'm not sure whether you're going to do it, but and I know you're going to say you were busy and you ran out of time, but if you don't practice these at home, you will blow them on the exam, not because you don't understand it, but because you punched it wrong in your calculator. So Google some examples and practice these. The reason I say Google them so you can check your answers. Okay? I am not going to be able to give you enough problems to check your problems on this because it's going to get down to whether or not you know how to use your calculator. Okay? And please don't ask me how to use your calculator. Okay? I do not use a scientific calculator. I either punch them in my apps, or Excel, or figure them out in my head. Okay? All right? So don't ask me that I punch it right on my calculator. All right? pH is always, absolutely always, pH is minus the log of the hydronium ion concentration. It's minus the log of the H+. That will never change. Minus the log of that value is what you have to get. So learn how to punch that in your calculator.
Because that makes it a positive, because pH is positive, correct?
It's always a value, yeah.
So yeah, the negative log, because you're going to have...
Oh, I see what you're asking. You're asking about the math part of it? Yeah,
Yeah, so
that's
that
correct. That's why you do, that's correct.
why it's negative.
That's why it's net, right. Right, that's how, when they solved it and derived it, it had to become negative, yeah, that's correct. And actually you can look at the values here and you'll know what they are. You'll get close on pH by simply looking at these values. But yes, that's why. Mathematically, that is why, correct. So it's always minus the log of that. So if you punch in a log and you got that number, you'd better change the sign. You do change the sign, however you're doing your calculator. Now, if pH is minus the log of H plus, or H3O plus, what's POH? Guess it.
Log of OH.
Minus the log of OH minus. Correct. You get it? Does everyone follow that? So if it says pH, you must use hydrogen ion concentration. If it says pOH, you must use the base. So if it says pH, you use the acid side. If it says pOH, you must use the base. Watch for that. That is a common mistake in this. Okay? If it says pH, you must use the acidic concentration, the acid concentration. If it says pOH, you must use the base concentration, molarity. Which means that if I ask for pH, or they ask for pH, and I only give you the base concentration, you've got to convert the base to the acid. You don't just use the base. You get it? You have to do the conversion. Does everyone follow? And you know how to do the conversion because we gave you this. Does everyone follow it? Because this is always what? 1 times 10 to the minus 14. You're going to see this on the slides, but I want to go over it first. This is always 1 times 10 to the minus 14. So if I give you the base concentration, you can find the acid concentration. Does everyone follow that? Okay? You're just going to be missing one of these. Okay? But I need to reinforce that because that's what's going to happen to you. On the exam, I'm going to give you OH minus concentration, and I'm going to ask you for the pH, and you're going to do the pH. You're going to do minus the log of OH minus. You're going to report that as pH. That is not the pH. That's the POH. you must calculate pH from hydronium ion concentration from the acid part of this. And I need you to practice those in your book or Google or somewhere until you get that concept in your head. Okay? I really want to emphasize practice these. Okay? Because you're not going to blow it because you can't do the calculation. You're going to blow these because you've forgotten to do that it's an acid or a base. All right? So we have it. So for the solution, minus the log of this comes out to 4. And you can look at the 4 that tells you this value. You look at your exponent, and you look at this value. They should be close. Okay? Like if this is 4 and you got something like 8 for your pH, you say, ooh, I punched something wrong. Okay? All right? Here, the coefficient, 1 times 10 to the minus 4. Notice it comes out to 4 here. Notice here, it's 2.4. It's to the minus 8. Look at this value. You get it? Pretty close to 8. I'm right. Does everyone see this? There's not much magic and not much else I can tell you about this. This is a matter of putting it, using the formula, and learning to use your calculator. Okay, I am not going to spend time teaching you to use your calculator. Please find some examples online to practice against so you can test yourself. You need to get a lot of these wrong before next week. Okay? So you'll know which mistakes you make. Here, pH. Okay, acetylsalicylic acid, aspirin. Okay, it's found from bark of a willow tree. If the solution has an aspirin concentration of 1.7 times 10 to the minus 3, what is the pH? pH is what? Minus the log of the hydronium ion concentration. Did I say this is acid? Yes. And it shows it is acid. Therefore, I can say minus the log of this number in my calculator, and I get this value. Here they show you all of these in terms of sig figs. This is an exact number. 2 sig figs. Exact here. By convention, okay, the number of sig figs in pH, this is by convention, is going to be the decimal carries the number of sig figs. You write the exact number and count the sig figs on the back there. You get it? The decimal carry, that is by convention. If for some reason you blow it in this class, I might be in a good mood. But I need you to understand that convention. Okay? By convention, the decimals are where you count the sig figs in pH. That is a rule. Okay? What is the pH of an ammonium solution with a hydroxide concentration of 3.7 times 10 to the minus 3? What do you do right away when you see that? I asked for what? pH. What do we use to do pH? Acid. What did I give you? So what do I have to do? Convert. Okay? Everybody still with me? I know I said pH. I have OH. I have to convert. How do I convert? You use this equation, and I will give you that equation. And you can put these on your cheat cards for the next exam. So I simply put it in and do your math. However you like to rearrange your math. I am not going to go over how to rearrange math unless you need me to again. Okay? I'm going to let you do your own rearrangement because some of you do. I've observed what you all do, and it looked like I have about 4 different methods of rearranging in here. Okay? All right? All right? If I see you put the values in the right place, okay, then I'm going to be okay with your rearrangements. If the values are not in the right place, I am not going to be okay with your rearrangement. Is everyone following? Okay? So here, we rearrange the equation, punch it through, 2 sig figs here, therefore the decimal carries what? 2 sig figs. Okay? This is developed for this method because of how the precision, the accuracy to which pH is required. Small pH changes are huge, particularly in the body. And therefore, this convention was adopted to allow for that sensitivity. Okay? So you write the exact number, and this carries the sig figs. POH. POH you calculate the same way as pH, but does it give you pH or does it give you POH? It gives you what? POH. You get it? POH, here, write this down, you're going to see it coming at you. POH plus pH equals 14. So if you know one, you got the other. You get it? POH plus pH equals 14. So if you count, I say, what's the pH of whatever? And you say it's 6. I say, well, what's the POH? Then that's 8. Get it? Does everyone follow that? POH plus pH equals 14. That's because the hydrogen ion concentration times the hydroxide concentration equals 10 to the minus 14. So the solution is, okay, a high POH. So if you have a high POH, you have a, okay, so you have high POH, you have what? Low pH. You have a high pH, you have a low POH. You get it? They're just the opposite. In the aqueous solution, here it is. pH plus POH equals 14, and POH equals 14 minus pH. You can do this in your head, right? Okay? In a solution, the pH is 3.50. We can calculate the POH from it. So 14 minus 3.50 gives you 10.50. Is there anyone who cannot do this calculation? Okay? You're free to put this on your note card. A few more slides to teach you about titration. Titration in a laboratory procedure is used to determine molarity of the acid. Molarity of the acid. But if you get molarity of the acid, you know how many, right? And it's water, you can do the 10 to the 14 trick. Uses a base such as sodium hydroxide in a burette to neutralize it. So we have an acid, and is this a strong or weak base? Sodium hydroxide, strong or weak?
Strong.
Does it? Very good. Conductor doesn't collect electricity. Weak or strong? Strong. If it's strong, it's strong. If it's weak, it's weak. Very good. An indicator. And the indicator is in there to simply tell you when you reach it. That's what it does. An indicator. Okay? All right? A lot of this is done electronically anymore. Okay? An indicator is added to the acid in the flask. The acid solution, phenolphthalein, is colorless. Phenolphthalein is in... I'll remember by lifetime. Over the counter. It uses an indicator. I've done it when I do STEM stuff, and I can't recall it. Okay. It's one of those blank moments. Change the color of the solution when it's neutralized. So it's basically there to tell you that it's changed. And this is used because of the indication that is there when you reach the pH. And that tells you about the acidity or the basicity of the species of the environment. Okay. Endpoint. Indicator has a permanent pink color. Molarity of acid is calculated using a neutralized equation. And so an equation like this, maybe we're going to have a problem like that. So here it is. We're going to titrate. Titration looks like it used our old good friend, didn't it? What is that? Our good friend dimensional analysis. Which we love.
Never say that again.
Which we love. Okay, if 16.3 mils of 0.85 molar solution is used to titrate HCl in this number, in 250 milliliters, 0.025 liters of gastric juice, what is the molarity of acid solution? So here the first thing we must do is what? Balance the equation. And then we carry out a dimensional analysis looking for what is the molarity. So molarity is mole per liter, right? So we're really looking for the moles, and we're going to take the moles and we're going to divide them by what? The liters. Does everyone follow what we're doing? So when you see this kind, you look for moles, and then you're going to take the molarity by divided by the liters. So the moles, and this is how we do it over and over again, and this is what we just did on the quiz. We take these. This is not a C1V1, right? C2V2. You take the liters, convert it, so you have the solutions here. This is converted to liters, right? This is all this did. We just changed the units because when I work with molarity, I have to be in liters. This is that step. Now we begin the real work. Liters to moles, mole per liter. That gets into moles. But this is the base, and I have to convert it to the acid. And this is that interconversion step that you always have to do when they're different. Moles to moles, over and over again. And where do we get these values from?
From your
Balance equation. Do we use the coefficients when we calculate these molar masses?
No.
Don't do that. Very good. We got that down, so I'm happy. All right. So here we have it, and we get this number of moles. Now that we have the moles, we take the moles and divide it by the liters. If I give it to you in milliliters, then you have to also convert it to liters, right? Okay? And we have moles per liter, and we get an answer, and then we get the sig figs, right? We did today. So let's see. This semester, I missed one sig fig, I think, so far, right? I always have at least one or two in there I miss. That's pretty good for me. Okay? For a person who can't count. Okay? All right? So it's pretty good. So always watch for that, though. Okay? That's how we do it. Okay? And there you have it. That's how we do these over and over again. All right? So what are buffers? Buffers help maintain that equilibrium, maintain that pH balance. You don't go too high or too low. And so a buffer is a combination of an acid-base conjugate pair, and that's why you've had to learn these conjugate pairs. A weak acid and a salt of a conjugate. And this is critical. So our buffers are from weak acids and salts. Keep that in mind. They're from weak acids and salt. Weak is the operative word. Got it? They are from weak. All right? And that's important to know. They are from weak, not from strong. Do not let me fool you on that one. Buffers are from weak. Weak, weak, weak. That means they're weak electrolytes. They don't conduct electricity as well. Okay? So you're not shocking your system. It's real mild. Chills. You get it? Okay? So when an acid or a base is added to water, pH changes drastically. To buffer the solution, a pH resists change. So this way, when something happens, the buffer is there to do exactly what it buffers the change. Okay? So you don't fall over and die. Okay? So the buffers are there. So the weak acid, weak base, buffered. Buffer system resists a change in pH by shifting equilibrium in the other direction. Say, wait a minute, you can't go that way. You can only go this way to keep it balanced. All right? Or keep the system balanced. I keep saying you, but it's really to keep whatever the system balanced. Given the Ka, do you know how to do Ka now? Mm-hmm. Yeah. Okay, and I keep rubbing it in. Very good. All right, this is where we want to be with this, all right? Given the Ka expression of weak acid, HA, conjugate base, you know how to do this. Products or reactants, it's a solid, you leave them out. Then you get this is the weak acid, the weak base, you get the values, you put them in. You can rearrange it, can't you? Ka is going to be a what? Constant. I have to give you Ka. Okay, I tell you what Kw is, it's 1 times 10 to the minus 14. But Ka depends on which acid. And I would give that to you. Okay? So in all of these, typically you're going to be solving for one unknown. And you're going to set the same equilibrium expression. And what I'm going to be looking for, just to pick on you a little bit, whether you say Ka, Kw, that kind of thing, that you recognize as an acid, or you say Kb, that you recognize that it was a base. Okay? That you recognize that it was water. Okay? All right? Follow? That's what we'll be looking for. Or is it just a simple, if it's a salt or something, you say KEQ or simply say K? Do you recognize that's what it is? Here, Ka of acetic acid is 1.8 times 10 to the minus 5. By the way, is this going to be acid or base? Yeah, the acid. Now, how do you know? The pH, if you see this 5, that pH is going to be less than 5 because it has digits in front of it. It's going to be 5 or less. So you can look right at the exponent and tell where your pH is going to be. So this is going to be less than 5 because it has digits in front. Okay, so this is 5 or less because it's 5. Okay, so right away I know my pH is going to be 4 something. Okay, it's going to be, you get it? So everyone follow right off the bat. What is the pH of the buffer prepared from this? So they say prepare the buffer. Do you care? You prepare it. You know how to write the KQ, the Ka. Okay, right? AQ. Do you write water? No. So these are all the givens. He likes to write these out in his textbook. This is what he likes to do. Okay, I don't require you to rewrite these out at all. We have to look at the balanced equation. Is it balanced? I hope so. And we write products, Ka equals products, molar concentration of the products, over reactants. In this case, it was balanced out. There are only ones here. We don't write ones. We look up K. I gave you Ka in this problem. So we look for the hydrogen ion concentration, or you put all the values in here and leave the unknown here. If you put the value here, the value here, and the value here, and you leave the unknown here, and you show me that equation, I will allow you to do your punch throughs, because all of you do them slightly different. Okay? All right? So here, we substitute. If you rearrange the equation and show the rearranged equation, that's even better. We put the values in. These are all ones. Wonderful. And so we do the pH minus the log of this on our calculator. Okay? And we get 4.74, which is the pH of that. So, blood buffer. Here's the example. Carbonic acid and bicarbonate regulate blood pH. This is important stuff here. So we have CO2. This is why you check CO2 levels. You'll hear them say, what's the CO2 level? You'll hear these things, right? Okay, and you hear them talking about this. This is why, because they work with the buffer. So you have CO2, carbonic acid. We get this equation. And notice here, is everything going to be using the EQ on this? Yes or no? Yes. So it's going to be all these products, all the reactants. Is the equation balanced? I don't know. Is it? Someone check it real quick. No? Okay. We'll see on the next page whether it's balanced or not. We'll find out, won't we? It's not. Okay. The equilibrium shifts toward the reactant. So when the body absorbs this, the reactant shifts toward the reactant, right? So you get absorbed the acid, it goes back the other way, right? Because say, wait, you already have enough over here. It goes back toward the product. When OH from foods and cellular processes is absorbed, it reacts and it shifts toward the product. So it says what? You're putting in more hydroxide, more base. Go, go, go. You get it? So this is why we check that. And I guess it didn't work. Any more problems? Shame on me, right? Okay, there you survived chapter 13.